Yeah, any questions you have about things that we have done so far? Okay, the question was about assignment or question was about if it's in an exam? Because this question is asked to 1 day before the exam, right? So that's why I'm asking. Because the answers are slightly different for both of those cases. No, not slightly, completely different for both of those cases. Okay, so the question was about Arrhenius law, right? So Arrhenius rate law will be given by, let's say, k equal to a naught e to the power minus e by RT. Okay. If we take logarithm of this, say minus e by r. Okay. If we were to plot ln k versus 1 by t. Okay. So, let us say this was y equal to a naught plus a1 x, that is a straight line. Okay. So, this is going to be a straight line which will go something like this, y like this, negative slope minus e by r. E is necessarily positive, r is positive. So, minus e by r is negative, right. So, now if 4, 5, 6 points are given to you, okay, you can do one of the two things. One is graphical method, or second is regression. Okay, that is basically curve fitting. Y equal to mx plus c, you have done curve fitting in the labs before, or you should have done curve fitting in the labs if 11th and 12th labs were not skipped. So, right. So, essentially that's how you would do it in an assignment. What about the quiz? Okay. If it's a quiz, then one of the two things would happen. It would be a case where once you plot or once you look at the data, if you spend some amount of time with the data, it would be reasonably obvious what the slope is going to be. Okay. So, then mathematics would not be the real math. The way the data for you was from some experiments, from some textbook, probably Davis and Davis, I do not remember now. Okay. But when it is an exam, it is going to be a fully synthetic data, so that the kind of uncertainty that is there in real experimental data will not be there for your exam, because exam is a 2-hour exam. That is option number 1 if multiple points are given. Option number 2 will literally give you 2 points. So, it is going to be fitting a straight line to 2 points, which is something that you would have probably done right in your 8th, 9th grade, right. What does that mean? If you take, so ln k is 2.1, I am taking any arbitrary number, okay. That is going to be a naught plus a1 multiplied by say 1.7 into 10 to the power minus 3, okay. And then temperature increases, that is why k increases. So, the k increases to 2.7 equal to a naught plus a1 multiplied by temperature increases. So, 1 by t decreases. So, it is 1.05 into 10 to the power minus 3, again absolutely arbitrary numbers, right. So, now you have basically 2 equations and 2 unknowns, and yeah, you are expected to solve linear equations up to 3 equations and 3 unknowns, or 4 equations and 4 unknowns as well. Okay, that is really reasonable expectation, I think. Okay. So, that is what the other type of problems will be. Okay, problems are going to be, you are going to have sub problems the way you have seen it in your assignments, which means the sub problems, they do 2 things. One, part marks, and second, it kind of gives you an approximate algorithm to follow. Okay. So, if I ask a question generically that this is the data, do something, that is a slightly tougher problem, because you now have to say do this, do this, do this, do this, you have to think about what to do. Okay. For step marks as well as for us to follow a little bit of an algorithm, most or several of the questions in the exam will be with multiple sub questions. Okay. So, that helps you understand where I am coming from for that particular question. Will all 25 marks be like that? No. Okay, because some of it is also about abstraction. This particular process of coming a problem statement to algorithm steps from a teaching learning viewpoint, it is called abstraction. So, abstraction is also an important skill, but abstraction is not the only skill. Recall is a skill, application is a skill, computation, that is one application is basically formula or whatever to figure out what to be used. The computation is how to use that. Okay. And abstraction is how to go from a generic problem statement to step 1, step 2, step 3. Okay. All of those are important abilities for students, and we are going to focus on all of those abilities. Okay. So, that is how the quiz is planned. Assignments do tend to focus a bit more on abstraction than the quiz would, a lot more on abstraction than the quiz would. So, therefore, you might find abstraction is something that should be doing in undergraduate, but lot of times with the boxed formula in the textbooks we end up not doing. Okay. So, that is one of the aims, to go away from boxed formulas, so that you can solve problems beyond the only exact problems that we have done in the class. Okay. That is the idea behind an education, especially a postgraduate education. Okay. So, that is my philosophy. I found that especially if there are students in this class who are interested in future in academic positions and being teachers and so on, some of these discussions might help some of you. Okay. Yeah, it is early days, but at least I remember the classes that I took very much in my second semester of my PhD, where one of the professors would talk about that. That helped me a lot when I became a faculty myself. So, maybe some of this thing helps you. Okay. So, what are the various skills that typically you want? Thereafter, it is comparison, and then there is design. This is the broad challenge that we want to solve. Okay. Not real grand ones are like global warming, challenge of water, all of those are grander challenges, maybe grand challenges, maybe smaller challenges, but how to go from there to a problem statement, that is another skill. That is what you begin to do in your MTech projects, and that is what you really focus on in your PhD work. Okay. So, this is about one type of thing. The other is, let us say we have this this is so Kmax or Km, that is Michaeli-Menten, right, or sometimes instead of Km they also write Rmax, as was there in your example problem or exercise problem, sorry. So, for this to linearize, we take 1 by R equal to Ks by Km this is A naught, this is A1. Okay. Likewise, if its reaction rate is R equal to K Ca to the power alpha Cb to the power beta, you can take a logarithm, and then that will get converted into a linear regression again. Okay. Okay. So, these are all the examples of related to the question that was asked, is if there is curve fitting type of a problem, what is to be expected? Okay, so slightly different answers for exam versus in general. Anything else? Not in exam. For the entire course, it's not on a bell curve. It's a shifted line, which basically means the cutoffs are based on the performance, but I don't fit the performance to a bell curve. Especially if lot of students perform really well, why should I mean, I'll be happy if there are if you earn 25 or S grades. If everyone is S and A, I mean, I'll really be happy. Okay, large classes and all, it does fall on closer to a bell, but I don't fit to a bell curve. Okay, and I try not to, based on the experience in the past, the cutoffs are predetermined, the upper end of cutoffs are predetermined, and I will not raise it beyond that. Okay, so the cutoff will not get, and again I'm not at liberty to disclose what the cutoffs are. You can ask about your marks, you can ask about each and every point that you got. You cannot ask about other students' marks. So don't bring me your friend's paper and do a comparison. If totaling mistakes are there, we will correct it. Okay, and unless there is a major blunder, if the totaling mistake is on the positive side, that's on us. Okay, we are very careful, so that won't happen. But why that is so is because, let's say there was an actual case of a totaling mistake, and the student got 17, and by mistake we had added it up to 18, and she came and said that, oh, there is a totaling mistake, it should be 17 and not 18. Like, lot of students would not have come to me with that error. Okay, so I'm not going to deduct marks for you. Fine, you earned it for your honesty, and since then I have not have stuck to that. Okay, I don't know whether that is right or not, but yeah, that's what it is. We are very careful. The total marks are checked by 2 people typically, so likelihood of error is low, but likelihood of errors is not 0. So if there is any error, bring it to our notice. Okay. Hey, all of that don't put on video. Where is he? Okay. So, and what else? Yeah. Be calm during exams. You know, it's okay. This is not a gate exam and so on, where you know, if one person wins, other person does not. Don't take exams like that. Okay, they're just a quantification of your learning. Yeah. Anything else? Okay. Yeah. So let us think of the picture that I had shown you earlier. The various pictures that I had shown you is, let's say there is a packed bed reactor, and in the packed bed reactor there are multiple catalyst pellets, and we are zooming in on a single pellet. Okay, so Sherlock Holmes is there. Yeah, is using a, it looks more like magic wand, but whatever, It's using it to zoom into the spherical pellet. This would be example of this. Okay. The other example that we talked about is a channel in the monolith where the catalyst is coated on the surface. Okay. Now, that case would be taken up as one of the cases. So, you depending on what the system is, you can either it can be of this nature or this nature. Okay. If it is of this nature, the idea is that it is not a full pellet, but it is this particular part is catalytic. Okay. Where are slabs used? Slabs and the cylinders are used in two different ways. Okay. Sometimes some of the advanced materials will take the material and we will compress them into either rectangular parts or we will compress them into cylindrical pellets. Now, why do we compress them in a particular way? Is because some of the materials, so one of the materials that I worked on when I was in the industry, okay, it was anisotropic, in the sense that I think I talked about that once. Okay, take the MOF material and you add some graphite to it and then you compress it, and the compression is in this direction. So, the graphite is not randomly arranged, but the graphite gets arranged more or less in the xy plane and hardly anything in the z plane. Okay, so, the thermal conductivity is very high in this plane, but very low in this plane. So, if I were to use, let us say, a pellet closer to a cylinder like this, what is going to happen is lot of heat transfer in this direction, but not enough heat transfer in this direction. Okay. So, the other option is to make pellet like this. The problem with a cylindrical pellet like this might be lot of heat transfer in this direction, but not much heat transfer up and down. So, if we wanted to use this, let us say if the reactor was this long, the entire cylinder had to be extruded to this length. Question is whether or not that material can handle that processing. So, if it cannot, then we will not do it. So, the solution that we came up with was to make a pellet like this, called a hockey puck pellet. This was in US. So, in US they used to do field hockey, not field hockey, sorry, ice hockey. So, ice hockey you might have seen those hockey pucks, right. So, that is why it was called hockey puck shape. The reason is because the thickness was done such that it compensates for the fact that heat transfer rate is much higher in this direction compared to this direction. Okay. This comes back to one of the questions that somebody had asked, is when we design all of these pellets, we are learning all of this in CRE course, but are these concepts are the ones that would be used in making the reactor? Not necessarily. It is not that these concepts are not used, but these are not the only concepts. The first concept that comes is processing of the material. If you cannot process the catalyst to make a particular size and shape, you will not be able to do it. The next thing that comes is structural stability. Let us say we have a large reactor and you pack the reactor with the catalyst pellet. The pellet over here has to bear the entire weight. Okay, because of the weight, if the pellet gets crushed, you are not going to do that. Okay, either we will make multiple plates in the reactor or we will make pellets in a different way, and that becomes the governing factor rather than CRE. Okay, so CRE will usually be the first case design parameters, then the rest of the things is going to be based on material processability and transport and structural stability. And once those things are designed, then you go back and use again CRE analysis, that for the new design does it meet the requirement that we had originally stated, and if not, then we cyclically go through that process. Okay, the interesting thing is the teams in industry working on these aspects are usually different teams. Okay, often there are times when, for example, the two managers will fight for this is the only way that needs to be done, otherwise reaction won't take place, is what I might say, and the other manager was talking about structural stability. They will say no, I cannot sign off on this because it is not going to give structural stability. Okay, so that's something that you don't see ever in academics, but you do see that, can see that in industry. If you are lucky, you will see that in industry. That is a very, very interesting problem, because then you are working on a design problem, and even at a higher level, because now you are designing based on multiple criteria. So, how do we design a system that matches multiple different criteria? So, very interesting problem. Coming to our CRE again. So, what we have is possibly different size and shapes of catalysts. The catalyst for the purpose of this module, the catalyst is porous. Okay? I am not saying catalyst is always porous. In fact, module 5A, we considered the case when the reaction is happening only on the surface. Now we are considering the case when the reaction is happening in the pores, ignoring external mass transfer limitations. Okay? That is what we will do in the first half or first 3/4 of this module, and in the last case we will just maybe have an assignment problem where we will say, oh, if there was external and internal diffusional resistances, then what happens? Okay? That is going to be our strategy for this module 5B. Okay? Important thing is the diffusivity, the coefficient of diffusion. Okay? Simple equation to remember, boxing the equation is 1 by d overall or 1 by d net is 1 by d, this is the molecular diffusivity, okay, and this is called as Knudsen diffusivity. Okay. What does Knudsen diffusivity mean? Okay. The pore, let us assume that the pore is cylindrical, okay, and the molecule is so small. Okay. The molecule will undergo Brownian motion and diffusion to keep going inside the pore. Okay. Particle or the molecule is small enough that it can't really see all the boundaries of the pore. Okay. So, if it goes into the center, it really can't see the boundaries too much. Okay. Think about it that you are sitting on that molecule and it is a foggy evening or foggy night or foggy day. So, you can't really see too much far away. Okay. This is when that molecule will be completely governed by this diffusion. Why? It is going to be completely governed by this diffusion because it cannot see or it cannot sense the presence of the wall. Okay. Now, you make these pores very narrow. Okay. Now, if the molecule is there, okay, wherever it is, it can sense one of the wall, presence of one of the walls. Okay. So, it is not freely moving inside the pore. Okay. It is moving, banging against a wall, moving again, banging against another wall, and so on. And if it moves like this, the movement is not gas phase movement. The movement is basically what is called as the diffusivity, the Knudsen diffusion. Knudsen diffusion has a particular formula, we will come to that soon. Okay. Now, this is when it is a cylindrical pellet, cylindrical pore. The pore is not necessarily cylindrical. Okay. So, let us say this is a spherical pellet, large spherical pellet, not large pellet, but we are zooming in into the pellet. Okay. So, okay, and let us say that this is the pore. Okay. So, you take a string, imagine a rope or a string, and you are inserting that rope or the string inside the pore. Okay. You take this blue rope and you stretch it out. The blue rope that is stretched out, let us say, becomes this long. Okay. Let us say that the radius of the pore radius of the pellet was capital R, okay, and let us say this length is LP. LP, oh LC, okay, LC divided by R is something called or LP divided by LC. Okay. So, the length of this blue string divided by the radius of the pellet or the characteristic length of the pellet is called tortuosity. Okay. We cannot directly use length of the pore because length of different pores is different, right. So, what we say is that the gas, instead of flowing radius, it flows tau multiplied by the radius, okay, and that has effect on the diffusivity. Okay. How does it affect the diffusivity? It just is a denominator, okay, and in the numerator you have epsilon, which is porosity. Okay. Now, what does porosity mean is, let us say we have a slab like this, pores are never going to be okay. This is pore number 1, this is pore number 2, this is pore number 3, this is pore number 4, that is not never going to happen, right. How will pores actually be? Okay. Let us say they were all very nicely ordered cylindrical pores. Okay. This will what the pores be. Okay. I will fill this up, this is where the gas is filled. Your epsilon is nothing but okay, and that is known as porosity. Porosity is a term that as chemists, chemical engineers, scientists, you are all familiar with. Okay. Porosity is nothing but the void fraction, is the ratio of, where there is nothing, means where there is just empty space, divided by the total volume, that is your porosity. Okay. So, the effective diffusivity in a catalyst pellet that we can use this we had talked about in module 5A. Okay. Where do you use it? We use all of this in the overall balance equation. The balance equation, we are going to make it for either this pellet or this pellet or this pellet. The balance equation okay. This is 0 because of steady state. This is 0 because of no convection. Okay. This is non-zero where D is going to be replaced by D effective. Okay. So, your overall model is therefore going to be 0 equal to okay, subject to boundary conditions, and one boundary condition definitely is Ca at R is nothing but CAS. Okay. So, spherical pellet Ca at R equal to CAS, slab pellet Ca at L or delta equal to CAS, cylindrical pellet Ca at again capital R equal to CAS. So, at the boundary, at the external surface of the pellet, concentration is equal to the surface concentration. Where is that surface concentration coming from? Just linking it to module 5a or module 5b. Okay. What we are going to do in the next class is not all of these derivations, we will directly go to the result, okay, where we will start with the definition of Affiliation modulus, okay, and we will talk about something called effectivity. Okay. I will go over the final expressions. We will solve I will solve one problem over here. Okay. On the class after next, we will do a tutorial. After the tutorial, we will go over the derivations. Okay. So, next class, summary of the final equations and me solving one example problem. The class after that, you solving tutorial problems, and the class after that, the derivation. So, hopefully switching this around might help our learning a little bit more, so that you see an example where this is applied and then we go back and derive the overall expressions. Okay. And again next time I will take feedback again to see how do you feel with the new approach, where we will solve problem first and derive expressions later. Okay. So, that is it I have for today. Saturday is your midterm exam. All the best, prepare well, and yeah, so let us hope we all do very well in the exam. Yeah, minute papers please. Yeah, thank you.